Okay. Hello, anybody and everybody that's there. Let me just get myself sorted a little bit. So, as you might tell from the description, and as I posted in my Discord a little earlier, I sort of didn't plan anything in advance that I thought, because sometimes if there aren't questions right away, I kind of I think about something neat that I've maybe looked at this week or something, and then I talk about that. But I didn't have time to think of anything in advance today. So we're coming in completely blind. But if anyone has got any questions they want to put in the chat or anything to talk about, then please do go ahead. But what I was thinking I would do in the meantime, until some questions come in, is look through a couple of physics memes on the Reddit r/physicsmemes, and maybe review them, see which ones I like, see which ones I don't like, and see if I understand all of them. Maybe there are some that are too abstract or too bizarre that I don't know what the actual joke is, but we'll see. Okay, so I'll start doing that. I'm going to look at some of these memes. Where? Let me just open it. Aha, there we go. Okay, you should be able to see my screen now. So this is just at the very top of the r/physicsmemes page. They've got this dude here, and it says, your teacher, when they start explaining that the particles and vacuum of space in our universe is filtered as waves from dimensions where time moves relatively faster. I don't think that's real physics. Maybe they're just explaining it in a particular way that will make it into a joke, but I don't think that's quite what this is about. Certainly there are, physics models that involve extra dimensions, and the idea of the vacuum of space-time is an interesting one, because these things are, the vacuum of space is not really a vacuum at all. Empty space and a vacuum is still full of particles popping in and out of existence. So the vacuum is an interesting concept. So that was the first meme. When you separate waves into categories like light or sound, wave is wave. I mean, yeah, the equations that describe pretty much all waves are fairly similar. You've just got different things waving. Water waves are water waving. Electromagnetic waves are electric and magnetic fields waving. Most waves are pretty much the same. I mean, some of them are quite different in character. Especially there are lots of these different wave configurations you can have in plasmas that are very complicated and have different polarizations, and different things are waving, the magnetic and the electric field, and I really don't understand half of that stuff about plasma waves. This one looks fairly long. The redder and redder, as if embarrassed to have done so. Oh, I see. Okay, this is funny. This is about how if you were to fall into a black hole, someone watching you fall into a black hole would see you approach the horizon, sort of asymptotically slowly. So they would never actually see you cross through the horizon. Someone watching you fall through. But what they would see as you approach the horizon is you would be kind of squashed down and sort of spread in like a sheet over the event horizon. And as you're falling in, the light that sort of would be emitted from you would be redshifted. So you would get redder and redder, according to the person that was watching you fall in. So I guess that is the joke on that one. I like that one. That's funny. Hey, you be more positive. Okay. Fair enough. Why is it a mushroom? Oh, because it's a mushroom cloud. Oh, that makes sense. Okay. Fair enough. Yep. Looks safe. I don't know what game that is. No clue. Always ignore friction. Indeed. That's good. That's a joke about Schrodinger's cat. You know, obviously. This thought experiment about, until you open up the box with the cat in, if there's some, you know, radioactive source or some quantum mechanical thing that controls whether the cat gets poisoned or not, you can't be sure whether it's, I mean, you know, to simplify, you can't be sure whether it's dead or alive. So that's obviously about Schrodinger himself in his coffin. Temperature is just a social construct. Negative absolute temperatures are infinitely hotter than positive temperatures. Do I understand that? I don't think I do understand that. Does anyone in the chat get that? I mean, obviously you can't have a negative absolute temperature. A negative absolute temperature is like a negative energy density. It's not a physical thing. I mean, temperature, in terms of like statistical mechanics, you can define it as like being this Lagrange multiplier that ensures the constraint that internal energy is conserved. So like maybe like a negative temperature would, you know. Yeah, I mean, this joke has also gone over my head a little bit. I mean, if something had a negative temperature, it's like it would take in all heat, even from the vacuum, because heat flows from higher to a lower temperature. Studied in solid state. Yeah, I mean, a negative temperature is not a physical thing, I guess, but I guess that's what the meme means. Oh, nice. An aerofoil. Cool. Yeah. Studying aerofoils was quite fun. We did that in our third year fluids course. I really like fluid mechanics. It feels like proper physics when you're doing it, because you have to think about all these different approximations and stuff, and you can really kind of picture what's physically going on in a system. Okay. Yeah, he didn't account for the acceleration of the lift. If it was moving up with constant speed, it would have been fine. Though this is more general relativity, not special relativity. Special relativity doesn't really deal with acceleration so much. General relativity does, though. This is sort of a nice way of showing the equivalence principle. That, you know, an acceleration is pretty much indistinguishable from a gravitational field. So this guy, when the lift is accelerating upwards, it's basically like he's feeling a higher gravitational field strength. So instead of 9.81 newtons per kilogram, he'd feel 9.81 plus the acceleration of the lift as the field strength. We are into memes, indeed, Alan MD. I mean, this is still technically the office hour. So if anyone has got proper questions, I am like ready at like a moment's notice to go back to my board. So just let me know, and then we'll still do that. But at the moment, in the meantime, we're just kind of reviewing some physics memes. Yeah, I think he probably lost it because he realized he was going to hit the ground, I think. Like, this moment here is when he realizes rats. And then, yeah. Memes are also proper, that's true. I mean, we're learning by memes, you know. We're looking at this meme and we're talking about the equivalence principle, that's learning. The first guy to sit under an apple tree was probably like, huh, nice. You know, apparently the tree that allegedly, because Newton was like a, you know, he was at Cambridge. He was a, you know, he spent all his time living and studying, working in Cambridge. Apparently the tree that allegedly the apple landed on is still there in Trinity College or something. But I don't know if they have any proof. I think they call it Newton's apple tree. But I'm sure there's no real historical proof that is the actual tree. I mean, I don't even think there's any historical proof that the story about the apple is accurate. I don't know. I've never looked into the historical sources about that. That's a good one. Yeah, you can't set pi equal to 3. Because pi is a dimensionless number. You can't, you shouldn't set a dimensionless number for 1. But if something has got dimensions, you can say it's 1. But pi is a dimensionless number, so no, you can't set pi equal to something else. C, sure, C has got units of, meters per second, so just define your distance and your time units such that it's one in those units, that's fine. But if you've got no units, you can't just change the value of something. Yeah, it did look like that neck was broken. Yeah, I mean, that's pretty accurate. If you've taken a quantum mechanics course, definitely the first thing you look at are these cervical radiculopathy secondary to whiplash injury. Is that your diagnosis? Where did you read that? It certainly did look bad, the guy in the lift. But yeah, this one is pretty accurate. Any quantum mechanics course you take, you always start off looking at the infinite square well. Which is a nice thing because in an infinite square well, your wave function has to vanish at the boundaries of the wall. Because the probability of the wave function tunneling through a wall of sort of infinite height, a potential well of infinite height, is 0. So your wave function has to vanish, and it gives you nice, simple, sinusoidal solutions if you've just got a normal constant potential with infinitely high walls to it. Did you miss the black hole stream? Yeah, the black hole one was the week before last. Yeah, that was the week before last. It's on my YouTube or something, so you can watch it then. Jonas Rydwald says, can you share your thoughts about bumblebee gravity? It's funny you ask about that, because I literally hadn't heard about bumblebee gravity until today. And then there was a paper... Yeah, it's on my YouTube, Alan, that's right. And then I got a notification this morning, like you can sign up so that you get email updates every morning of all the new papers that are posted on the archive. And I was reading through the abstracts of some of them, and there was one that mentioned bumblebee gravity. But that was honestly, that was the first time I'd actually heard of it, so I really don't know anything about bumblebee gravity, I'm afraid. Yeah, apologies. I can't remember what the I can't even remember what the paper was. This was a different paper I saw on the archive about cosmic strings. I have a bit of a side interest in cosmic strings, so this one caught my eye, but I haven't got a chance to read it properly yet. It seems like it's about making non-local modifications to GR, and I mean, I don't know. Introducing non-locality in physics is always a little spooky. This meme is about the J psi particle. Yeah. We had quite a lot of problems and stuff about J psi and its decays in like our 3rd year particle physics course. Honestly, I can't remember much about it though, but it always seemed like a weird name for it. But yeah, I'm pretty sure this was really important in proving all sorts of things and about strangeness and stuff. So I'm pretty sure the J/psi is a strange particle. I may be wrong though, I can't remember actually. I'm not a phenomenology person, so I don't know this particularly well. Send SS to your engineering friend. Oh, okay, nice. That took me a while to get that meme. I'm being really slow today. Yeah, you can't set pi and e equal to 3. You can set dimensionful numbers to 1. You can set the speed of light to 1, that's fine, because it's a choice of units, but you can't set pi to 3. Pi is dimensionless, so it's not proper to set it to a value other than pi. That's a good one. Yeah. I mean, every resistance is probably pretty important if you're a pilot. I mean, what would be worse if like you assumed inviscid flow or something, and then you put them in the plane, because viscosity in Bernoulli's principle is the whole reason planes go up. The whole reason you get this upthrust from the wings. So if you assumed inviscid flow, you couldn't ever have a plane flying. Why does pi exist? Well, pi. Now I can show my. Oh no, that's the wrong thing. I can show my whiteboard. Well, pi is the ratio between the circumference and the ratio and the diameter of a circle. So for any circle you want, if it's got a length around it, the length of the circumference. Come on, draw a circle. If I hold it, sometimes this thing does a circle. There we go. If this has got length c and the diameter is length d, then pi is defined as this ratio of the circumference to the diameter. And it's a constant for any circle. Okay. How do they fly upside down? Well, the wing shape doesn't change. Like, as in it's. Well, I'm pretty sure the end of planes' wings are like, they've got like paddles on that can go up and can go down. So I mean, I think this sort of the angle of this thing here determines, like if the thing is down like this, the plane will have like a net up thrust. But then if the tip of the wing is in this position, it will have a thing upwards like this. So if you just flipped a plane upside down like that, it would start to go down. So they have to adjust the fins and stuff or whatever, so that it doesn't just go down. But yeah, that's a good question. So yeah, I'm sure that the pilot would have to do something in the cockpit to make sure that it doesn't just fall down, so it can go upside down. Wait, what? I don't get it. Oh, wait, I've just realised I was opening a meme, but I forgot to close my... Hang on. Okay, there we go. I don't get this meme. When you're not looking, when you are looking. Yeah, I don't understand this meme. Does anyone else understand this? Is it like a quantum mechanics-y observer effect thing, or... Yeah, I'm not sure I understand that meme. Oh well. I knew we would find quite a few that I didn't understand. Unlike military figures, commercial planes do not have engine power for sustained inverted flight. They rely on lift from the wings. Yeah, that makes sense, I guess. I mean, you don't really ever see commercial planes going upside down. Because when they're going, obviously the wings are built as aerofoils such that they're better at producing an upthrust in a particular direction. So there's only so much you could change by having the wings tilt backwards or whatever these pads do on the end of them. Okay, that's a fun one. One of his favourite insults was to refer to people he didn't approve of as spherical bastards. Because they were bastards no matter what way you looked at them. That's good. I like the word curmudgeon. That's a really nice word. GW, as in gravitational waves. Yeah, we could talk about gravitational waves. I think that would be a nice thing to talk about. Maybe like, because I think, so we missed the last Saturday's spacewalk thingy, because I just didn't have time to get it all sorted out in a way I was happy with. So this Saturday we'll talk about white dwarfs like I was hoping to last Saturday. And then maybe the week after that we'll come back to black. I mean, there's so much to talk about with black holes. That's the thing. So we talked a little about black holes. But, you know, we could spend another Saturday talking just about information and stuff about black holes. And then maybe after that we could do a calculation, you know, trying to think about gravitational wave spectra of things. Because this is gravitational waves are quite related to my research too, actually. I'm interested in the gravitational waves that would be produced by phase transitions in the early universe. So it's quite a different mechanism to how, you know, the gravitational waves are produced by like black hole mergers and stuff. But maybe we could look at black hole mergers, because I think that's probably the more interesting one anyway. Alan MD says, you think it's because of the square cube law where... Oh, right, the square cube law where the matrix errors in this case becomes viscous because of their size. Talking about fairy flies. Yeah, I'm not sure I follow what you mean. Yeah, that sounds like engineering talk to me. I'm not sure. What did it... Q sent me. Oh, I see. Yeah, topical QAnon joke. Physics textbooks. That's a weird position to be in. Nobody should be in that position in like an elevator shaft or something. Also, what is wrong with that guy's like torso? His butt is so perfectly angular. Oh well. Physicist on Valentine's Day. Nice. Calculating talk. Lots of fun. I don't get that. Young's modulus. That's stress over strain, isn't it? So... Oh, I see. It measures toughness. Ah, okay. Of course. Oops, that was my email. Shouldn't have clicked on that. So Young's modulus measures toughness. That's right. The book is from Concept of Physics by H.C. Verma. Wait, which book? Oh, this book. Oh, okay. Fair enough. The exam won't be that tough, and they give you this one. Wait, I swear I've seen this question before. That looks like a question that was on like one of my undergrad mechanics exams. It looks weirdly familiar. But as far as I can remember, we didn't have like 7 questions per paper. So I guess it can't have been, but that question definitely looks really familiar. High school physics be like Newton's law of gravitation applied to all bodies irrespective of their size. Yeah, I mean, that of course is not true. If you go down to quantum mechanics, Newtonian gravity definitely doesn't work. And if you go up to, like we saw when we looked at Mercury's orbit, if you go up to even things like the Sun and Mercury, Newtonian physics also doesn't quite work then. There's things it misses. You need general relativity on very large scales, and eventually for thinking about gravity on very small scales, you need quantum gravity, whatever that might look like. I mean, I get this one. I get that, you know, I cross J is K, but I just don't get why. Why have they got like the sad Doge bonking King Kong and Godzilla? Fair enough. Memes are weird. Jack and Joe leave their homes at the same time and drive towards each other. Jack drives at 60 miles per hour while Joe drives at 30 miles per hour. They pass each other in 10 minutes. How far apart were Jack and Joe when they started? Oh, okay. Fair enough. Oh, we've seen that one. Repost. Oh dear. Hello, Slayer Darth. We are currently doing office hour, but while there are no questions, we're reviewing some physics memes. Teach you some stuff. Well, at the moment we are learning through memes, but if you've got specific questions, I do have my whiteboard hidden underneath. Someone asked about pi earlier, so that's why that's there. So please go ahead if you've got a specific question. Feel free. When you get negative temperature but the exam is in kelvins, something's wrong, I can feel it. Yeah, absolutely. Ah, absolutely, get it? Because absolute temperature scale. Nice. Atwood machines with massive pulleys, physics undergrad sanity. Oh, yeah. These are these things where you've got like pulleys attached to pulleys. Yeah, that's horrible to look at, all of that stuff. Sigma notation. What, you mean like summations? Like wait, where is my screen? There. As in like this kind of thing. Like this? Is that what you mean by sigma notation? I think that's what you mean by it. If not, let me know. But yeah, this is a shorthand for writing down summations. Your understanding is that if you have the sigma symbol, a number at the top denoting a limit, and a variable statement at the bottom denoting the starting number of the variable. Yeah, exactly. So, you know, as an example, say I wanted to do I equals 1 up to 3, where ui here denotes some sequence of numbers, where which number I'm looking at is labeled by this index I. Okay, we call this index I a dummy index because its only purpose is to label which sums we're adding up. Okay. So for example, if you were summing up from I is 1 up to I is 3, that's just I1 plus I2, sorry, U1 plus U2 plus U3. If you were summing up from I equals 4 up to 7, then now you don't start at 1 anymore, you start at 4, and the last one you go up to is 7. Okay. Yeah, that's right. I is well, is an integer in this case. Yeah. Well, in this case, starting at 1, it's a natural number. Sequences generally, if you're doing sequences in maths like this, I will be not just an integer; it'll be a natural number. So it will be like from 1 upwards. But you know, often physicists will do sums where we might have negative indices as well in the sums. Like if you're doing you know, like a discrete Fourier transform or something, you'll be summing over from minus infinity up to infinity. Exactly, natural numbers are counting numbers. So the natural numbers are, you know, 1, 2, 3, ... 137, ... forever. Okay? Whereas the integers could be, you know, ... minus 42, ... minus 101, ... 68, ... forever. Negative and positive whole numbers, okay? And yeah, the natural numbers are then the counting numbers. But you know, it doesn't matter. All that you have to look at is you have to look at the dummy index, I, which tells you which ones you should run through. and then the lower limit that tells you when you're running through the i's, you should start at 1 and go up to capital N, okay? Reminds me of Einstein's summation. Yeah, Einstein's summation is, you know, it's a convention where, say you wanted to write the sum from I equals 1 up to some whole number n of like each term in a sequence multiplied by another term in a sequence. So, you know, say you've got two sequences A and B, where A is like A1, A2, blah, 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 up forever. And B is like B1, B2, B3, and so on, also up forever. And say you wanted to multiply the first term of both sequences and add that to the second term of both sequences and add it to the third term, where these first and first, second and second, and third ones are multiplied together. So that's how you would write this in the sigma notation. But then Einstein's summation convention basically just says you can draw this and ignore the sigma. And it says wherever you see two same indices together, where these two things are multiplied, then you just will assume that there is a summation there that is summing over all the available indices. I mean, technically the Einstein summation one, because it's in general relativity, where you have these, you work in terms of contravariant and covariant components, what they're called. So then actually you wouldn't sum over this. You would need to have one of these would have to be an upper index and one would have to be a lower one for you to sum over them. Okay. You've asked a Discord friend to mute you on the server until you can solve a maths problem he sent you. It's an optimization problem. Given U is blah blah blah, budget constraint blah blah blah, maximize utility. Okay, so you want to maximize U is 10x squared y, and subject to 5x plus 10y equals 1000. Okay, so the best method to use these things is the method of Lagrange multipliers, if you want to look that up. But what you essentially do, without going into quite why it works, the method is you introduce a new variable that we call a Lagrange multiplier. So I'm going to call it L. Why not? And now what I do is I try to, instead of trying to maximize U, I now try to maximize U minus L times by the constraint, where L is this new variable I've introduced. Well, also what I have to do to the constraint is I have to rewrite it so that it's something equals 0. Okay, and then I take the thing on the other side of the equals 0 and put that inside here. Okay, so this is my new quantity to maximize. Instead of trying to maximize U, I'm now trying to maximize this whole thing here, U minus L times the constraint. So I'm going to call this thing, let's call it M. And now I just treat this like it was any ordinary calculus problem. So for example, say you wanted to maximize U without this constraint, then the way you would do that would be to find when du by dx was 0, and also when du by dy was 0. I mean, technically I should draw these as partial derivatives, where when you're differentiating with respect to x, you keep y constant and vice versa. But now to maximize m, I've introduced a new variable. So all I have to do is to also say that this whole expression m is stationary with respect to varying L. So in other words, this thing has a stationary point when dm dx. Why did I write s when I said x? Dm dx is equal to dm dy, which is equal to dm dl. Okay, yeah, this is a Lagrange multiply method. You still need to differentiate though, like Matthew D. Pariah said. So let's substitute in what we actually have for u. U is given by this expression here. So just writing m in terms of x's, y's, and l's, we have it like this. And now we just have to do these three derivatives, and that'll give us when this thing is stationary. Now, of course, once you know it's stationary, you then still have to show that it is, whether it's a maximum or a minimum, because there might be multiple stationary points. But I think actually in this case, actually no, in this case there will be, I think, multiple stationary points. So if you differentiate this whole thing m with respect to x, you get 20xy minus 5l, and that is 0 from this first equation here. Then if you differentiate the whole thing with respect to y, you get 10x squared minus 10l is 0. And then if you differentiate the whole thing with respect to L, now if you differentiate the whole thing with respect to L, you actually just get back out the constraint equation you had before, which is encouraging because it still tells us that the constraint equation is satisfied. But of course the L we introduced now appears elsewhere too, and that should be 1,000 up here. Okay, so now we've got three equations and three variables, so you just have to solve these equations for these three different variables. Okay, so first I'll take this equation. I can rearrange this for y. For y, this becomes 100 minus a half x. Then if I want to, I can take this equation for y and put it back into here, and then I've got an equation in terms of x and L here, and then after eliminating y, I've got another equation in terms of x and L, and then you can do it. Okay, you think you've got it from there. All right, great. Yeah, this method of Lagrange multipliers, it's really useful, you know, in general to for doing this. What is this? 3.14 and 3.15. This is just linked to, I don't know what this is. It's not linked to a specific document. It's just linked to a Dropbox with a few things in it. Is it this black hole perturbation theory one? 3.14 and 3.15 in that? 3.14, 3.15. You found it difficult getting started in calculus, but you're mostly self-taught. Yeah, I mean, calculus is not easy, for sure. Yeah, it's not easy, but it's incredibly useful once you've kind of mastered it a little bit. You can do an enormous number of new problems when you've learnt calculus, including these optimization ones that are very useful. Wait, where? I can't find this equation you're talking about. Oh, oh, right. Oh, I see. Oh, I see. Okay. Right. What are these? Oh, these are these scalar fluctuations of a metric? Okay, you've got the Klein-Gordon. Actually, what I can do is I can put this over here. Then can you see this? If I... You can, but it's slightly to the side. Okay, let me download it and then I'll open it. Wait. Let me open it first. Okay, and then I will go to that. Okay. Right, you should be able to see that okay. So you say you're looking at 1.4 and 1.5. Did I do further maths at A level? I did indeed. How much is both similar and different to A level maths? Well, the further maths, I mean, the A level maths has most of the calculus in it. The further maths just has maybe some more stuff on like complex numbers, and like Taylor series, which is related to calculus and is a very important thing to look at. But there's not a huge amount more calculus in there. 2.1.3. Wait, so let me start from the beginning. Okay, so here is the Klein-Gordon equation in curved space-time. And what they're doing then is, it looks like now they're finding solutions to the Klein-Gordon equation. So you weren't, so you're happy with 3.13. 3.14, now this looks just like a standard kind of solution to like if you've seen Laplace's equation, which is like where you have the Laplacian of something is equal to 0. That's Laplace's equation, where you can expand your solution in terms of these Legendre polynomials and this phase factor here. So these are actually the Legendre polynomial times by this phase factor is exactly the spherical harmonics. So I think you asked the question a little, well, you posted something in the Discord a while ago about a different equation where they'd expanded things in spherical harmonics. So this is the same thing, except they've just written the spherical harmonic explicitly as these Legendre polynomials. Oh, actually, P is Lm. Legendre polynomial is just L, isn't it? Oh, you found it hard to solve for EM and gravitational perturbations. Well, this stuff is still scalar perturbations. I don't think this has any of the gravity stuff in it. Yeah, I think this is still just scalar perturbations to the black hole. Was there a section later where they talk about? Oh, here's the electromagnetic perturbations. I mean, this is stuff I'm a lot less shaky on. I mean, a lot more shaky on. These perturbations. Yeah, this stuff I'm really not sure on. I'm not sure, sorry. I don't think I can help with the EM and the gravity perturbations. Yeah, apologies. These ones are out of my comfort zone. Maybe I might go and look at a couple more memes again. I want to look at some more memes. How do I... Ah, there we go. And do that, and then do that. Okay, there we go. Back to memes. If you have any other questions, please do let me know. But yeah, sorry I can't help you with the EM and the gravitational perturbations to that metric. Electromagnetism, thermodynamics, EMF, thermo, quantum mechanics. Yeah, I mean, fair enough. Quantum mechanics does change both of those things quite a bit. No problem. Thank you. Wait, is that's not even a meme, that was a advert. Trying to calculate the positive divergence of people in a bar when I start talking about Maxwell's equations. Oh, that's sad. If a vector field has got positive divergence, it means the fields are moving away from a point. In general, there's like a net flow away from a particular point. So this meme is saying if you start talking about Maxwell's equations, which obviously use things like divergence a lot in them, there'll be a flux of people away from you, which is sad. I used to find it nice when I was in I don't know, nightclubs and stuff, thinking about how the motion of people in a dance floor where they're dancing very violently, like people in a mosh pit, motion in a mosh pit is very well approximated by a Maxwell-Boltzmann distribution. So, you know, if you have an enormous mosh pit with many people, the people in there, their motion is basically in a Maxwell-Boltzmann distribution, which is quite funny. Which is the same distribution that describes the speed of particles colliding with each other in a gas. Obviously, a very high density a high density gas with people being that close, but still, that's quite funny for me anyway. Yeah, I mean, that's pretty accurate. 85% of the universe is made up of dark matter, and we've got no idea what actually dark matter is, if it even is, a substance, or whether it's something just where gravity needs to be modified on large scales. Personally, though, I tend to favour it being a substance rather than, it being some sort of matter rather than some modification needed for general relativity. I mean, who knows, maybe it's a bit of both. Bethesda physics or something, I don't know, I'm not a gamer. Yeah, I don't get that reference. But this is about quantum tunneling. A particle on one side of a barrier, even though technically it doesn't have enough energy to tunnel. They've written E is greater than V here. That seems... Oh, well, actually, no, I mean, that's fine. But even if it didn't have enough energy to penetrate this potential well to get through this wall here, it would still sort of tunnel through but decay exponentially, the probability of finding it on the other side. Yeah, I mean, that's pretty true. The postulate of special relativity is that the speed of light is a constant in any inertial reference frame, whereas general relativity, the key is the equivalence principle, which relates, or which tells you that you can't tell the difference between gravitational fields and just ordinary acceleration in space-time. Acceleration and gravity are really the same thing. Locally, anyway, you can, tidal forces are like an effect that will be felt on matter if you have, a larger matter distribution, something that is extended, then the gravity will vary on it. So, like, if you have something in a radial, spherically symmetric gravitational field, if it's very long, then part of it will all feel the gravity moving towards the center, but if the thing is very long, then one end of it will feel the gravity pulling it slightly this way, and the other end will feel the gravity pulling it that way. So if you have an extended object, you can tell the difference between an acceleration and a gravitational field, which is why it's important in the equivalence principle, or the strong equivalence principle, to talk about local observers. You understand how to write the Maxwell equations in tensor notation? Ah, okay. Well, oh, much better. You can hear me. Yeah, I don't know why it did that. I mean, I listened to it myself. It seemed to be doing the same thing that it does when I for some reason when I change scenes and stuff, it does weird stuff where I have the same audio track between different scenes that I don't understand. But I didn't actually change any scenes that time, so I'm not sure why it went crazy. Who knows? Oh well, it doesn't matter. What was I saying? I was saying, oh yeah, writing down Maxwell's equations. So this contains... What does this contain? Does this contain everything you want? I think this contains all of Maxwell's equations. Oh, can I start from the first line? Oh, well, so this is this anti-symmetric Maxwell tensor, which you define in terms of this vector potential A, and then we're taking these 4 derivatives of it. Okay, so you can tell it's antisymmetric because if you swap the mu and nu indices, you end up getting minus the thing you had before. Okay, and this thing is, because it's totally antisymmetric, it's got 3 components, which it should do because you know, it has it should contain information about the electric and the magnetic field, which are both 3D vectors, so it should have sort of 6 lots of information in it. And then if you take the 4 derivative of this, in the vacuum, this thing is 0. And this contains Maxwell's equations, or, well, I think maybe not all of them. Maybe it's only Gauss's law and the divergence of a magnetic field one it contains in it. I think there's another one that involves the dual tensor, which looks like which is like the contraction of the Maxwell tensor with the Levi-Civita tensor. And there's another equation involving this, but I can't actually remember. I can never remember these things off the top of my head, which one they are. But that's sort of roughly how this covariant formulation of electrodynamics works. Yeah, apologies. I have to try and look at these equations beforehand because I forget what they actually are. Now, this is only in a vacuum. If you had like a charge or a current source, I think then instead here you would have something like J nu for a current source, and there's a prefactor, and I think the prefactor is mu naught, where mu naught is now mu is the mu here is not an index. This is the permeability of free space, one of these constants associated with the vacuum. But yeah, I can't remember exactly what these equations are. I always forget these. But I hope that makes some kind of sense. You can, there are all of these special relativity textbooks have got a lot of details about the covariant formulation of electrodynamics. So I want to look at another couple of memes, I think. Okay. Has that mucked up my audio? No. Okay, I'm glad that didn't. Something weird was going on with my audio. Maybe it is from where I flick between these things. I'm not sure. Oh well. Electrons can exist at any distance around the nucleus, Niels Bohr and S. Rutherford. We don't do that here. Okay, yeah. Well, that is how, without quantum mechanics, it looks like matter should just sort of emit like radiation. When you accelerate charged particles, they emit radiation. This Cherenkov radiation. So an electron orbiting around a nucleus, because it's undergoing circular motion, it's accelerating, should emit radiation and lose energy and eventually spiral in. But then Bohr and Rutherford and others had this idea about quantum mechanics where you can, if you quantize the angular momentum, this is kind of how quantum mechanics is all introduced, this idea of quantizing angular momentum. And if it's quantized, it has to be non-zero, actually. The minimum angular momentum you can have corresponds to like wrapping 1/2 wavelength or something around this circle in the Bohr model of the atom. Okay, someone's posted a rap. I'm not gonna watch that. Okay, gang, let's see what C really is. Ah, yeah, very nice. Another relativity meme. I mean, I don't know. I mean, C is 1 even if ds isn't 0 though. I don't know. Oh, I see. They've even commented, guys, chill. It's the simplest coordinate independent definition. Oh, okay, fair enough. Conservation of momentum. What's going to happen to this guy? Oh. I didn't expect that to happen. Nice. He reached up with the ball, put momentum upwards, and then thought he had to have momentum coming down at his feet and went through the chair. Sonic the Hedgehog is blue because of the Doppler effect. Well, that would only work when he was running towards you. When he was running away, you would see him red. So, I don't know. Has anyone ever seen Sonic run away from them? Is that not a thing? Does he never appear like that? Maybe fan theory. Well, not fan theory because I'm not a fan, but theory. Maybe Knuckles is just Sonic running the opposite direction. He's red. Who knows? Yeah, that's good. Units are very important. Absolutely. We had in one of our tutorials in first year, we had our tutor talking about special relativity, and he was trying to justify to us that setting C to 1 was a totally justified thing to do, because you can just pick your unit system such that it's the case. And he was like, "Oh, it doesn't matter what you measure C in. Meters per second, cats." Like, he just screamed cats in this really comical way that amused all of us. Anyway. But yeah, it's very true. Choose whatever units you like, it doesn't matter. Isn't there a quote or something that says, like, all units are equally absurd or something? I can't remember what the quote is. But yeah. Celsius or Fahrenheit, Kelvin. Yeah, I really don't know how actually to convert to Fahrenheit. I've got no idea how that temperature scale works, to be honest. I only know Celsius and Kelvin, of course. 90 degrees Fahrenheit users. That's hard. Nice. I do appreciate a prequel meme. Notice that it's a vector equation. Wait, what? I can't see this. Yeah, I can't even see that equation that is on the book, if there is one. I wonder if it's a joke about that. I think there's a t-shirt you can buy or something that they sell at MIT that's like, it's got Maxwell's equations, actually written in the form we were just looking at them. And it says, like, and God said, let there be light. Because the Maxwell equations, of course, predict the existence of electromagnetic waves like light. Ah, that's controversial, yeah. I do prefer also this notation here, putting the integration variable before the integrand. But throughout school, we always did it like this. But then I think someday it just happened that every book I was reading happened to use it like this instead. And it does make a lot more sense when you think about it, because it's telling you immediately once you're reading from left to right which integration variable you're supposed to be integrating with respect to. But, you know, it's a personal preference, I guess. Humans are complicated. They do things cats can't understand. And then someone has written down the Schrödinger equation. Nice. You've seen... There are so many books where they don't include the triangle law of vector addition, which makes a student think electric current is a vector. Wait, what? So many books where they don't include the triangle law of vector addition, which makes a student think electric current is a vector. I'm not sure I follow what you mean by that. I mean, current density is a vector, like electric current density. You can write that as a vector, and in fact you do in the Maxwell equations. That appears as a vector. Yeah. My kidnapper returning me after listening to me talk about entropy and the heat death of the universe for 8 hours. Sounds good. Quantum physicists. Huh. Yeah, that's cool. Yeah, if you make an observation, it's, you know, like if you have an electron beam or something, and you're firing this electron beam at these two slits here, you would expect, and if you're making an observation about which slit the electron passes through, then you get this kind of pattern where it looks like a trickle of kind of solid particles passing through and impinging on this panel here. But if you're not making an observation, and by observation I don't mean like just looking at it, I mean making a measurement, like having some particles interacting with it, which of course you do when you look at something. You have to have light bouncing off of it, but it doesn't have to be going into someone's eye. There's the sentience of the observer or otherwise has no effect on this. But anyway, if you're not making a measurement of it, then you get this diffraction light sort of like pattern here, where these electrons are behaving like waves rather than up here where they're behaving like particles. Only current I, not density. Oh right, yeah. Oh yeah, current I isn't a vector. Yeah, it's like the integral of the current density. So yeah, that's definitely not a vector. Okay. Oh, a solution to the ultraviolet catastrophe. I almost didn't read that second line. Yeah. That was again one of the original motivations for quantum mechanics, solving this ultraviolet catastrophe, which just sort of happened to be solved. I think Planck realized it was solved if you quantized angular momentum of these particles, which he did, and then it sort of gave all of quantum mechanics in quite an indirect way. Gauss is the belle of the ball. Ah, okay. Is this how a Poisson distribution approaches a Gaussian distribution when when you've got like a very, very large number of possibilities, a large number of possible outcomes? Or is it large, or is it a short, oh wait, that's a binomial distribution. Or is it a large number of or is it a small, like, I can't remember Poisson distributions very well. Poisson distributions are about like finding the probability of something happening in a given time interval if you've got like the average number of times it happens in like a certain interval or something. I can't actually remember. My statistics it's been a while since I did any of this sort of statistics. When you are dead from the inside, yet you are still alive. Ah, this makes me think of my friend Liam. Liam, are you watching at the moment? If so, this makes me think of you. You are watching. Nice. Assume the penguin is a circular cylinder. That seems reasonable. Penguins are pretty axially symmetric. Albert Einstein, when he proved general relativity, even if people criticized it. My goals are beyond your understanding. That's not particularly funny, though. Wait, what? I don't get this meme. Some of these memes are weird. Oh, 420. I see. Right, Kirchhoff's junction law. We've seen that one. Nice. That's good. Also true, physics is very open source. I mean, apart from like journals where you have to pay to access things. But I mean, for the most part, physics is pretty open source, which is good. Yeah. Scientist calls the Higgs boson the God particle. Yeah, I don't know who because I mean, people really don't like the term God particle. I mean, it is a stupid term. I don't know who first called it that, but I imagine that person, whoever they are, probably got a bit of flack for it, because it definitely got perpetuated in the press afterwards. Oh yeah, I've heard about this paper. where Alpha and Gamal were writing a paper, and they just added beta because it looked funny. I thought that they like invented a physicist that didn't even exist to do it, but I guess they didn't. I've not really heard of Alpha, actually. I think I assumed it was the other way around, that they invented, or they brought someone called Alpha on, but it looks like they were one of the actual people that worked on the paper. Pi is 3. Again, not true. How Heisenberg stated the uncertainty principle. In terms of momentum, we have no position. That's a nice way of stating it, actually. My non-physics friends when I tear apart sci-fi movies. Fairly accurate, I guess. I don't know, I tend to get annoyed at people that do that, though. Like, I don't know, it's fairly fun to talk about it, I suppose. The science they get wrong, but just enjoy the film. You don't need to, like, Neil deGrasse Tyson it, which is quite annoying. Yep, that's true. Physicists do definitely steal quite a lot of maths from mathematicians. Well, not steal, but, you know, adopt. Ah, interesting. That was a similar one to one we saw earlier. I think I prefer that one, actually. This one. I mean, to be honest, that is my brain when I finish a very short calculation. That's my brain before I even begin the calculation. I need a lot of breaks. Wait, what? Is that real? Surely that's not real. Conductivity is... Don't they use sigma for conductivity, not the ohm? I mean, that would be cool if they did use that, to be honest, but... yeah. The average engineer has literally a genius level. Oh dear. This dude is... I assume it's a dude because of what they're saying, but this person is a little bit salty. Huh. Fair enough. Me trying to figure out who formulated Feynman path integrals. To be fair, the history of that is quite confusing. You know, like, there's Feynman, there's Schwinger, Dyson, Tominaga. They've all got fingers in those pies. It's quite difficult separating who did what. Well, anyway, maybe we will leave it there with the physics memes if there are no other things coming up. I realise I've just got an email I actually need to reply to. So I guess I will leave it there for now. Thank you for coming along, those that did. I'll see some of you on Thursday, perhaps, where I'll play some Mario Kart and we can chat more about physics a little bit. So okay, thank you for listening, and I'll see some of you then. Okay, bye.